Hi everyone. So in our last video, we were exploring our model comparisons and looking at the effects of coding the time variable with either the initial time point coded as 0 or the central time point coded as 0. And we saw the effect that that had on the intercept. And ultimately, the important thing to remember there is it really matters what 0 means in your time variable. And there are going to be situations where it's better to code the central point as 0, and there are going to be situations where you might code the beginning as 0. There might even be situations where you code the end point as 0 and look backwards in time. We decided ultimately that for our purposes, we wanted to focus on coding the starting point as 0. So our initial time point is 0 in our models, and then we're looking at how the Roche-scaled FIM scores change over time from that central starting point. What we're going to do now is actually look at fixed effects that are conditional and how that's going to affect our intercepts and our slopes. And what we mean by a conditional fixed effect is, does our estimate for the fixed effect of the intercept and does our estimate for the fixed effect of time change as a function of what group you're in? So in our data, we're going to be looking at a person's AIS grade and looking at, are they an AIS category C 1 to 4, an AIS category C 5 to 8, or paraplegic, and how does that shape their data? Do people who are in one of those categories show a lower intercept? Do people who are in one of those categories show a faster rate of change? And are those things correlated with each other? So by plugging the fixed effects into our models, we're actually going to build a series of models to show you how you can control this and actually add in very specific effects that you might be interested in. So looking at the data, our first conditional model, we're going to have a person's Roche-scaled FIM scores as a function of a fixed effect of year, and we're using year.0 here again, and their AIS grade. And note that in the middle here we have a plus. So this is not an interaction between these terms, it's just we have a main effective year and a main effective AIS grade. Ultimately, this is equivalent to AIS grade interacting with the intercept, because we're going to estimate three different lines for the different AIS grades. So again, we'll place our cursor on that first line of the code. We'll hit Control Enter or Command Enter if you're on a Mac, and that will run our linear model. You can see down in the console window we don't have any errors or warnings, so everything seems to have been processed successfully. And then we can get a summary of that model printed to the screen. We'll focus in for now on the fixed effects of the model. You can see that it gives us a fixed effect for the year, a fixed effect that says AIS grade C 5 to 8, and AIS grade paraplegia. And the reason for this is that in R, it will default use what people call treatment coding or dummy coding, in which it takes one reference group and codes that group as 0, and then each other group is coded relative to that reference group. So this is worth stopping and talking about for a second, because what group is coded as 0 matters in much the same way as what 0 means for your time variable. So right now, you can see that we have grades C 5 to 8 and paraplegia. We don't see one for C 1 to 4, and that's because C 1 to 4 is our reference group. So then when we look at the intercept, this is actually the intercept for the reference group. So this is the estimated value for participants in the AIS grade C 1 to 4 at the beginning of data collection. The effect of AIS grade C 5 to 8 then is the difference between C 5 to 8s and C 1 to 4s at the intercept. So people in grade C 5 to 8 are actually 8 points-ish higher than people who are in grade C 1 to 4 at the start of data collection. Similarly, our paraplegics are 16 points higher than people who were in grade C 1 to 4 at the beginning of data collection. You'll notice, however, that for the moment we just have one fixed effect for year because we didn't allow year to interact with AIS grade in this model. So our model is currently estimating one slope for all three of the different groups, but it's allowing them to start in different places. Next, we can actually build the interaction model where we have conditional intercepts and conditional slopes. So in that model, it's very similar, right? We're looking at Roche-scaled FIM scores as a function of year.0 and AIS grade. But notice that here we're using an asterisk rather than a plus sign. So this asterisk tells R we want the sort of the fully orthogonal set of effects. So we're going to get a main effective year, we're going to get an AIS grade, and we're going to get an interaction. If we wanted to just have an interaction without the main effects, we can put a colon there. That's not recommended. If you're going to have interactions in your model, you always want to at least have the main effects. But as you build more advanced models, there might be situations where you want, maybe some two-way interactions, but not like up to a five-way interaction, so you can control exactly what interactions you add in. For our purposes right now, we'll use the asterisk because we want to add in both main effects and the interaction into our model. Our random effects stay the same, where we have a random intercept and a random slope for each person. We'll run that model, and then we'll print this summary model to the screen. And the first thing you'll notice is that our fixed effects have expanded significantly. Again, we have an intercept, and we have a slope. So these are the intercept and the slope for the reference group, which in our case is people with AIS scores of C1 to 5. So in people in AIS C1 to 4, their intercept is 20 points, and they are expected to improve at a rate of about 22 points per year. People who are in AIS grade C5 to 8, they have an intercept that's about 7 points higher. So their intercept is about 27.8 points, and they improve at a significantly faster rate than the reference group. So this 15.89, that's the difference between the slope of the paraplegic group, or sorry, excuse me, this is the intercept. This is the difference between the intercept for the paraplegic group and the intercept for AIS C1 to 4. So the intercept again for AIS C1 to 4 is 20.1, and our paraplegics have an intercept that's about 35.9, right? So quite a bit higher at the beginning of data collection. Down below that is where we actually see the interactions between year and the individual contrasts. Okay, so this is our time by AIS grade C5 to 8 contrast. So this value is the difference actually in the slopes now. So this is the difference between the slope for people in AIS grade C5 to 8 and the slope for people in AIS grade C1 to 4. So our reference group slope was 22. The grade C5 to 8 are about 4.7 points higher than that. So they have a slope of about 27. They improve by about 27 points per year on average. Similarly, 7.257, that's the difference in the slope for paraplegics and people in the AIS grade C1 to 4. So our reference group had a slope of about 22.34. The paraplegics are 7.26 points higher than that, right? So about 29 and a half points per year is the rate of improvement we expect for people in the paraplegic group. Now, we do get t-values and p-values for these individual contrasts, but one of the first things we should actually interpret before we look at those contrasts is this model as a whole a statistically better improvement than the more compact model? So we can do that using the ANOVA function, and we can compare our two different models. So we get that output down below, and again, we're going to look both at the deviances and the AICs. So when we look at that, we can see that there is a change of about 5.23 points in the deviance, and there's 2 degrees of freedom here because we have 2 extra degrees of freedom in our augmented model compared to our compact model. And that is not statistically significant, assuming we had an alpha of p equal to 0.05, or alpha equal to 0.05, right? Because the p-value in this case is 0.07. Similarly, when we look at the AIC, we can see that the AIC does go down slightly for this model, but it is not a large change in the AIC. Different resources will suggest different cutoffs for the AIC that you should use, and you can somewhat map these on to measures of effect size. I don't know that there is a sort of universally accepted cutoff for the AIC, so in general I tell people to just decide what your AIC criterion will be in advance. And you can also go more into detail here using things like the AIC corrected rather than the raw AIC. But if we were just looking at this, this is a pretty limited change in the AIC. Now, it might be the better model, but if you, for instance, had set a criterion of 2 points, which is one that we often use in our work, to say that we have to see at least a 2-point reduction in the AIC, just to be a bit more conservative, this would not cross that threshold. So arguably with this linear model of time, we don't really see a statistically significant improvement by adding in a conditional effect for the slopes. Now, again, that's going to depend on exactly where you've drawn your AIC cutoff. And if you just say, well, we'll go with the AIC and the lowest AIC, we would accept the conditional slopes model. If we're being more conservative about it, we would not accept the conditional slopes model and we would stick with the conditional intercepts model. So this is one of the nuances of some of these model comparisons that as you're building these models in practice, you'll want to read up on and look at the different decision criterion that you might want to make. And do you want to use the AIC or the AIC corrected? It's probably a good idea to use the AICC, but for simplicity's sake, we have not done that here. So finally then, the next thing that we want to do is actually plot the fixed effect estimates from our models on top of the raw data to show the conditional effects. I am actually going to go with the conditional slopes model here, in part because those weren't the last two models we went to compare, and we're going to continue building on these things. But also sometimes it can be informative to show an effect even if it was not statistically significant. For instance, if you had a variable of theoretical interest, people might really want to see that data. So we're going to create a plot here to show the raw data with the fixed effects overlaying on top of that raw data. So I'm going to go and plot G4. And what you can see are three different groups in the different facets or panels of our plot. Each individual is shown as a collection of gray dots over time. So that sort of scatter plot is really useful for people to see some of the variability in your data and get as close to kind of the raw data as possible. And then we're plotting the fixed effects from our simple linear model over the top of that. So we get a unique slope and intercept for the C1 to 4, a unique slope and intercept for C5 to 8, and a unique slope and intercept for our paraplegic group. And obviously these things are going to line up because I calculated these lines based on the fixed effects, but it is worth sort of going back to your fixed effects and just making sure that when you build a plot, it shows what you're actually seeing, right? And we saw a higher intercept for the C5 to 8s than the C1 to 4s, a higher intercept for paraplegics than the C1 to 4s, and higher slopes for both of these groups relative to the reference group as well. So with this plot then, we can kind of visually and qualitatively see what we were trying to quantify in our multi-level model. And building forward, we'll expand on this model, and we're sort of keeping this conditional slopes model for now. In the next video, we're going to talk about evaluating the statistical assumptions of our model, which is important for not only sort of looking under the hood and seeing what the raw data truly look like, but it's also important because if you want to calculate something like a p-value, right, those things are based on certain parametric assumptions about how the residuals of our data are distributed. And that's one of the key points that we'll emphasize again in the next video. But these assumptions have to do with our residuals. And when we have multi-level models, remember that you have residuals at multiple levels. In our case, we have residuals at 2 levels. We have individual errors at 1 level, and then we have random effects and how individuals deviate from the group norm.